As I said, today's webinar is closely related to modeling of for durability studies or some accidental effects which may appear on reinforced concrete structure. The topic is corrosion and fire effect on reinforcement bond. We will be mainly focusing on the bond modeling because the webinar is the second from our series about bond modeling, about reinforcement bond modeling. Maybe some of you joined our webinar last month when we discussed the basics of modeling of reinforcement bond. And today we will go a little bit further in the details and into some specifics related to durability studies. So, as probably many of you know, we in Czerwonka Consulting are developing software called ATENA, which is dedicated to modeling and simulating real behavior of concrete structures. And for that purpose, we need to be able to model the real material behavior, which means all the nonlinearities which appear in reinforced concrete structures, meaning, for example, crushing of concrete due to exceeding the maximum compression stress, or cracking of concrete under tensile loads, or when it comes to reinforcement, it's reinforcement yielding or rupture, or even the topic of today, which is the bond modeling, which can simulate the slip between the reinforcement and the concrete itself. So the scope for today, I will start with some brief introduction about the reinforcement bond modeling. It will be a very brief summary of the last webinar, and then I will move to modeling reinforcement in durability analysis, more specifically in a chlorized induced reinforcement corrosion, where, as you know, the corrosion can reduce the bond between concrete and the steel. So even this can be simulated in ATENA. And then I will be speaking about reducing the bond, how to implement reduction of bond properties in fire analysis, because as in the case of corrosion, the bond can be affected and significantly deteriorated during the fire. So at the beginning, I would like to summarize briefly about the reinforcement bond modeling in ATENA. Basically, there are two main cases how the discontinuity between the stress transfer between the steel and the surrounding concrete can be somehow disturbed. First one is the cracking of concrete itself. This is if you use the nonlinear material model in ATENA, this is always presented in the model, and if the concrete cracks, there is not perfect transfer between the stress from concrete to the steel reinforcement. Or there is another option available for the reinforcement material, and if you activate the bar with bond material prototype, then one additional degree of freedom is added to the reinforcement to the reinforcement material. This additional degree of freedom represents the slip of the concrete embedded in the slip of the reinforcement embedded in concrete. I'm sorry. And this is one additional degree of freedom for the analysis to be determined during the solution. As it also adds some additional compliance to your model. So often, if you try to fit some, for example, experimental study and you study results, and you observe that, for example, the stiffness of your structure is a little bit higher than you observed in the experiment. I mean, the numerical obtained results are have a little bit higher stiffness than obtained in the experiment. Somehow, sometimes it can be a good idea to implement this reinforcement bond modeling, because it often somehow reduces the stiffness of the numerical model. If you imagine a short bar embedded in concrete, as shown in here, and there are different forces acting at one end and in another, it's kind of natural that the difference needs to be somehow compensated and transferred through the friction stress to the concrete. This is very general formula how to calculate the friction. During the analysis, it's this process is, and the evaluation of the bond is done in every single node of the reinforcement, for which we defined the bond slip law, which means the relationship between the bond stress and the bond slip. And at each node of the reinforcement, this relationship is evaluated and it's calculated, and we check if this condition for slip is fulfilled. The friction is calculated from 1/2 of the reinforcement. I mean, from both sides of the reinforcement, from half of the element size. So this gives this part of the equation the right-hand side. This gives the cohesion, and the left-hand side of the equation is the difference in the forces in the reinforcement. And if this is determined, if this shows that there is a reinforcement slip, then through iterative process we find the equilibrium, which is and now you can see two additional terms in the equation, where K is the stiffness of the reinforcement, and S are the slips at both sides of the element. And when this condition is fulfilled, we find the equilibrium. As today I will be talking only about the reinforcement, which is modeled as 1D tension compression elements. It's the basic reinforcement type available in ATENA. And if you define this material in the element geometry tab, you choose the bar with bond geometry type, and after that, bar with bond tab pops out, and you can define the relationship for your for the bond properties. As I mentioned earlier, this bond strength is evaluated through the as a friction along the bar, for which we need the bond strength and we need the bar perimeter. You can also define if any of these of the ends of the reinforcement are fixed with respect to the surrounding material, which means that if you choose that one or the other end of the reinforcement is fixed, or both ends are fixed, at this one node there will be no slip allowed, which is very beneficial if you model, for example, if you model some reinforced concrete structure with end hooks, and you don't want to model the detail of the hook at the end of the reinforcement. So very often engineers use this kind of option to set it as fixed. or it's used when modeling, for example, pull-out experiment in ATENA, when you add some load plate at the end of the bar and through which you apply the displacement or the force, and you don't want this end loading plate to slip with respect to the bar, so you also use this kind of option. Again, I would refer to the previous webinar available on YouTube, where this is discussed in more details. Also, for the bond properties, there is available temperature, corrosion, and location dependency. Basically, in these functions, you can by this option you can define relative functions to multiply the maximum bond stress and the bonds or the bond slip function. Those are relative functions, so either in terms of either as a function of temperature or corrosion degree or the location, I mean the length of the reinforcement. Some of the bond functions based on some literatures or standards for designing of reinforced concrete structures are already implemented in the GID software, which is used as a preprocessor for ATENA. So you can automatically generate the bond slip function, meaning the relationship between the bond slip and bond stress. And this is for generating of this function, you need basically you need to know only the type of the reinforcement and the strength of the concrete and some bond quality, for example, according to the FIB standard. And then the software can automatically generate you the function. So I think this was covered in the last webinar. This was only the quick summary, and now I would like to move to the reinforcement bond in durability studies. Maybe some of you know that since ATENA version 5.7, we support durability studies, mainly ASR degradation of concrete, reinforcement corrosion due to carbonation and chloride attack. Generally, today I will be mainly focusing, or the example which I will be showing comes from its simulation of a chloride attack on reinforced concrete. And in such an analysis, typically we assume that that the chloride attack is composed of several stages. At the beginning, at the beginning we have some induction phase. This means the moment when the chlorides penetrated the microstructure and the front approaches to the reinforcement. And this stage ends with so-called depassivation of the reinforcement, when the concrete will no longer provide effective protection against corrosion, and the corrosion of the reinforcement is initiated. It is defined through some critical chloride content, and at that moment, when the critical chloride content is exceeded, the propagation phase begins. At the propagation phase, the reinforcement area is being reduced, and we also and the model can quantify the amount of cracks in the concrete cover and the moment when the spalling of the concrete cover occurs. Since the spalling of the concrete cover, we assume that the reinforcement corrosion continues under the environmental condition, and and if no actions are taken to prevent the worsening of the condition, a collapse of the structure occurs. So this is basically the main idea behind the model implemented in ATENA. And if you want to do such an analysis, usually you make a model of your structure, you apply some general stress, general loads, and which induces some let's say stress state level cracks, which then accelerates this first induction phase, the phase when the chlorides penetrate the structure. Then there is some kind of chemomechanical aging model where at each step you firstly calculate the increase of the crack width, and then through the chloride diffusion model and reinforcement corrosion model, you get the updated section area of the reinforcement. This in return will worsen the resistivity or the load-bearing capacity of the structure, or increase the crack width, and so on, until you reach some state, some age of the structure where you want to evaluate its ultimate load-bearing capacity, and at that moment you somehow terminate this step and go to simulate some kind of load test to get the load-bearing capacity of your model. Maybe at this moment I would like to briefly show the theory of the chloride diffusion model, as I think it's pretty standard way how to evaluate the diffusion process, because probably, as you know, the chloride penetration into the microstructure is often simulated using diffusion equation, which has time with time variable diffusion coefficient to account for the somehow for the binding of the chlorides into the microstructure of concrete. So if we solve this diffusion equation and get the solution in 1D, we obtain this form of equation where the chloride content at given depth under the surface and time depends on the boundary, on the chloride content at the boundary, the diffusion coefficient, and here we can see this term represents the crack width, which accelerates the process. The diffusion coefficient itself, it's in time, it's evaluating according to this relationship. And once the chloride content at the reinforcement position exceeds the critical chloride content, then it's assumed that that the corrosion is initiated. After that, this is the end of induction phase and the beginning of propagation phase. From that moment, the rate of the reinforcement corrosion is calculated. It depends on the total chloride content, on the temperature under which the structure is exposed, on the ohmic resistance, and on the corrosion time. based on that, we calculate the depth of the corrosion at each reinforcement bar and the effective diameter, which is given by which means the diameter of the uncorroded reinforcement area. Finally, this leads to occurrence of crack because the corroded reinforcement is larger in volume than the initial steel. So this leads to some buildup of the internal pressure and cracking of the concrete cover. We implemented the model from the Duracrete project, which was a European project aiming to enhance the durability of reinforced concrete structures. And based on this, we calculate the moment when the spalling of the concrete cover occurs. After that, it's possible to input the corrosion rate at the environmental condition. So from the moment of the spalling of the concrete cover, the constant corrosion rate under environmental condition is used. If you want to learn more details about this corrosion model, I would like to bring your attention to this paper written by my colleagues from Červenka Consulting in collaboration with the Czech Technical University, where you can find some case studies and applications of this model to real concrete structures. So maybe I forgot to mention at the beginning that that at this webinar is also also this is a chance to ask questions if you have any challenges or any issues when using our software. So for that moment, I will dedicate some time at the end of the presentation, or you can type them into the chat box, and my colleague or I will answer them either during the presentation or at the end. I will check the chat box right now if I see. Sorry for the delay now. Oh, now I see that somebody has a problem to see the presentation. I think it's hopefully solved by now. Now Rad asks, it's a private message, so I'm not sure if you can see it all everybody. If the load history is important when doing the doing the durability analysis, yes, the loading history is very much important because as I said, it takes for the calculation of the diffusion process and penetration of the chlorides into the concrete, we need to know, or you need to somehow include the effects of the existing cracks, of the effect of mechanical cracks in your model. So firstly, you should load your structure to some general service state level to get the crack width, and then apply the chloride attack model. Now I would like to show some application of this corrosion model. So this shows some simulation of the experimental study of a pull-out test. Let's assume that we have a concrete prism with the dimension 15 to 15 and the length of 30 centimeters. And the embedded length of the reinforcement is 25 centimeters. The bond slip law is generated based on the FIB model code, and from one surface we apply the chloride attack. Based on my understanding on what usually happens during the pull-out test, there are 3 possible outcomes. What will be the result? If the concrete is the weak factor, there will be some splitting failure of the concrete and sudden breakout of the, or if it's a more massive concrete, there will be a sudden breakout of the concrete cone. Or if the steel is the weak link in this system, what might happen would be that the steel will start to yield, and finally it can rupture. Or if there is some poor bond condition between the concrete and steel, this bond will fail and a slippage of the bar will occur. So those are 3 possible outcomes. All of them can be simulated in ATENA. Maybe those of you who joined the last webinar remember this slide, and it says how to determine your failure mode, how to see what happens in your model. So if it's the concrete breakout or the splitting failure, you will probably see some formation of a big cracks and sudden failure. It's on this LD diagram, which shows the relationship between the displacement of the loading plate and the pull-out force. It is the green the green curve, which shows somehow sudden failure. In case that the rebar rupture, you will see, and you plot the strain in your reinforcement, you should see some quite large strain. And also on the LD diagram, here it's represented by the red curve, you see the typical characteristic of the reinforcement. So at some load level, the reinforcement starts to yield, and then at the end we see the rupture. And finally, if the failure mode is the slippage or the bond failure, the variable you should plot in ATENA is the bond slip, and compare it with the bond slip function you defined. And typically you, on the LD diagram, you will see something which resembles the bond slip function you give to the reinforcement. So in this case, it's the blue curve. So in this case, we have our concrete specimen a little bit larger, and at the beginning I will present the results of the pull-out test without any reinforcement corrosion. So in here, based on the shape and based on the screenshots from the analysis, we can see that the failure mode is the splitting of concrete. At the after exceeding at the peak log, we can see the massive crack formation inside of the concrete specimen, and finally formation of this kind of longitudinal crack and splitting failure mechanism. Also, which is also one more thing which is worth to note at this image is that this is some kind of the parameters of this analysis were chosen to show some interesting behavior. So the stress in the reinforcement bar is about 500 megapascals and very close to the yield strength of the reinforcement bar. So the question now is, what happens when we start when we apply some corrosion model and start to simulate the reduction of the reinforcement area due to chloride-induced attack. For this case, for this analysis, we used this kind of literature data, which was published as a review study of several experimental results, and finally they suggested this kind of relationship based on the regression analysis, where from about 3% of reinforcement corrosion, the bond strength is significantly reduced, and we can see that around 30% of the reinforcement corrosion there is no bond strength, no residual bond strength at all, almost based on this model. Also, maybe some of you from your experimental studies know that at the beginning there is some increase in the bond strength due to the densification of the interfacial transition zone between the reinforcement and the concrete. However, this is not reflected by this model. Yeah, because it's somehow conservative, and it should be always on the safe side for the analysis. So this relationship based on this paper was inputted in the corrosion dependency. So as you can see, this is the function of the corrosion degree, and this is the relative value which is used to multiply the bond strength defined in the function for bond slip. So and then we simulated somehow accelerated reinforcement corrosion test, applying the corrosion from one side of the model, and given the conditions, I mean the diffusion coefficient and the chloride concentration and the boundary, after 30 months we observed that the reinforcement corrosion degree is slightly above 4%, and the failure mode changed due to the reduction of the. Maybe you remember that when there was no corrosion, we observed the slippage failure mode, and quite high stress in the reinforcement. Now, due to the reduction of the cross-sectional area of the reinforcement, what happens is that the reinforcement yielding occurred. Lower area increased the stress even higher, and now the reinforcement yields before the concrete breaks. Sorry for a second. Also, what you can see that somehow the stiffness here is lower, and even maybe the peak load is higher. That's somehow maybe not so intuitive, and we need to dig deeper in the model details to explain this behavior. But what happens here is that not only the reinforcement area is reduced, but also the bond properties are reduced since we define this kind of relationship. So we are at the beginning of the degradation of the bond properties, which means that effectively the bond is weaker. We can see it here, which leads to the fact that we activate more of the concrete inside of the specimen. We can see that the cracks inside are formed in larger volume, which slightly increases the strength of the concrete, and we see the higher pull-out load. Now I show some summary of more data. This shows the corrosion for 30 months, for 24, 30, 36, 48, and 60 months. The first two gives the concrete splitting failure mode. It showed on we can see typical load displacement diagrams for this type of failure. The other two, they show the reinforcement yielding and then rupture. And after that, if the corrosion takes longer, we can see that the bond becomes the weakest link in the system, and reinforcement slippage occurs. This kind of example, it was chosen to demonstrate these three types of failure mechanism. They are all very, very close together. So if some reinforcement corrosion occurs, we can easily skip from one mode to another. In here, this diagram shows the corrosion degree as a function of time for the curves on the left diagram. At the beginning, until 2 years, we see the concrete splitting. Actually, for almost 1.5 years, nothing happens because the chlorides did not yet reach the reinforcement, so there is no corrosion. And from this moment, the reinforcement corrosion starts and gradually increases. After 2 years, we observed that the mode changed from concrete splitting to rebar yielding, and after 3 years, the bond slippage occurred. Those are these two curves. So that was the end of the example for the durability analysis. And before moving to fire analysis, I will check the chat box if we have some other questions. So Rad asks because previously there was the question how the load history impacts the analysis results, and so that the answer was that we need to take into account the load history in our analysis in order to be able to account for the impact of mechanical cracks for the diffusion problem. So the question now is, so what if we don't have the history of our infrastructure? Yeah, actually, what one option can be to use to use some standards. For example, in some cases we know what should be the what is the characteristic load, and and based on the statistic we can calculate what's the usual load level in our structure. Also, so this could be one answer, and yeah. So generally, the cracks can also occur in some accidental moments. For example, sometimes in the history there was overloading which induces some cracks, but those cracks then they can close after unloading. So generally the answer would be to use the something what we might expect as a standard or service life load. Another question is that if can the model code bond model be formulated as the interface element to be used in similar analysis in bond studies of 3D solid elements? Yeah, so this question aims to the moment when we don't use when we don't simulate the reinforcement as 1D elements, but if we simulate it as in 3D, use it solid elements, and then we add between the concrete and the reinforcement some additional finite elements simulating the interface. So if I want to use the model code, I don't know if there is any straightforward way how to do it, but maybe I can fit the interface properties based on the results. I mean I can simulate the load test to obtain the relationship and fit the interface properties to obtain the relationship according to the model code. I hope it was understandable. So what I mean is to create a model, model the interface using the interface elements, and try to fit their properties in order to obtain the result according to model code. That might be the way. So now let's go back to the fire analysis. So this somehow summarizes the workflow how to do the transport analysis in ATENA, how to do the fire analysis in ATENA. At the beginning, we need to solve the transport problem to get the temperature distribution in our structure during the accidental situation. For that, we use the transport module where we create a model and usually solve the unsteady heat transfer problem, applying the appropriate boundary condition, and then exporting the results for their later use in the static module, where we simulate either the resistance of the structure during the fire or the residual load-bearing capacity after the fire. In the static module, we need to be careful to load the data from the previously conducted transport analysis. Also, we need to define the temperature-dependent material behavior and also the temperature-dependent bond behavior. So firstly, in the transport analysis, we even have a special boundary condition for simulating the fire inside of the structure. You can either input your own values, meaning the temperature and at the surface and with respect to time, or you can use some code-based functions which are already implemented in the software. Then the second step would be to define the temperature-dependent materials. The temperature dependency is now available for concrete material, for reinforcement, and for 3D solid material. The 3D solid material is not shown in this slide, but basically the idea is very similar as for these two. The temperature dependent materials are hidden in the material definition under the material prototype. So you need to choose the material prototype with the temperature dependent properties, both for concrete and reinforcement. And then a new window pops out where you input the function for elastic modulus, tensile strength, compressive strength, etc., as a function of temperature. Because as we all know, the material properties, the concrete material properties, are reduced under elevated temperature. So this kind of relationship can be inputted here. Then, if we use the bond properties, we can also input the temperature dependency for the reinforcement bond, which is also negatively influenced by the increased temperature. For example, here we show the data from this paper, which shows somehow gradual reduction of bond properties from approximately 200 degrees C up until 800 degrees C. Then now I would like to show some analysis results. This actually comes from the example which is included in every installation of ATENA. Normally you can find it in this path, in this location on your computer. So you can open it and run it by yourself and look into more details. And now this video on the right side shows the temperature evolution during the fire. The fire boundary condition is applied to the bottom surface of this element. This element represents 1/2 of the beam subjected to 4-point bending. So now we see only the symmetrical half. And here we see the temperature evolution at the bottom surface and on the top surface. So this will be the first step done in the transport module. And then I will take this result and import them into the static module and to investigate how the elevated temperature affected my model. On the right side of this slide, we can see 3 different cases. The top case shows the analysis without the elevated temperature. Normally, under the given load, we would have approximately 90 megapascal stress in the reinforcement. Now we have. Please, please, can you mute your microphone? Now there is somebody with the microphone on. Anyway, let's continue. So under normal cases, there would be about 90 megapascals in the reinforcement during the given load, under the given load. If we simulate the fire impact and don't activate the bond temperature dependency due to the reduction of the material properties, both for reinforcement and concrete, but excluding the bond, the stress in the reinforcement will increase to about 285 megapascals. This maybe to be more specific about this image, the colors in here they indicate the temperature in the reinforcement. So the maximum temperature here it's about 556 degrees C, and the distribution under the reinforcement gives shows the stress along the bar. So it increased from 90 megapascals to about 285 megapascals. If we activate the bond temperature dependency, the stress is somehow redistributes and decreases to a maximum 259 megapascals. If we look at the maximum stress in the bond between the concrete and reinforcement, if the bond temperature dependency is activated, it goes to maximum 2 megapascals, and somehow some oscillation occurs how because of the slippage of the reinforcement during the fire. But if we don't use this option and don't account for the negative impact of the temperature on bond, it goes up to 4.5 megapascals. So this can be a conclusion from such analysis. I guess now we have 5 more minutes left, so I would conclude with this one, and I would like to thank you for your attention. Sorry for presenting on wrong screen at the beginning, and please, if you have any question, you can unmute your microphone and ask, and I will try to answer it, or you can type into the chat window. So now we have a question. If the interface can simulate the temperature-dependent properties. No, I think it's not available now yeah, at this moment the interface cannot model the temperature dependency. I mean, we are talking about the interface elements in the not used in these examples. I didn't show any model with the interface elements, but in some other examples, when we want to somehow simulate the cohesion between 2 different materials, we have special interface elements in ATENA. So but at this point they don't have the temperature dependency, or at least it's not available from the GID preprocessor. Another question is from Sasan. That based on his findings, the bond models are usually stiffer than the experiment. If there is any solution for that, we usually often when we try to fit the numerical data to the experiment, we need to be very careful when conducting the experiment in order not to have some additional compliance when measuring the response. It is some kind of compliance in the machine or in the support, which then needs to be, if this occurs, then it needs to be taken account also in the numerical model. I don't know if Sasan can provide any example of that, or maybe I remember something from our hotline support. By the way, if you are using ATENA and you are users with valid maintenance, we provide some hotline support for you. So if you need if you have some troubles with modeling, you can send us email on cervenka@cervenka.cz. I mean cervenka at cervenka.cz, and we will try to help you with your modeling. I will type it into the chat box. Also, now we have some cloud service where you can which you can use I think for some initial analysis for free, and test whether test some modeling in ATENA. So also, if you are interested in this service, feel free to contact us. Another questions, is there anything for the concrete side to consider for the corrosion related effects? No, on the corrosion on the concrete side, we don't consider any impact of corrosion, because the primary effect is the reduction of the cross section area of the steel, and for the concrete, I think there is nothing much happening under. I mean, there is some aspects from the cement chemistry, but not severe degradation. Okay, so I guess 1 hour is gone now, and as there are no further questions, I would conclude the seminar today. Again, thanks for joining, and I hope we will see each other in some next ATENA webinar. Now we are preparing one for you, one last webinar from the series of modeling bond, and it will focus on bond modeling when in pre-stressed concrete structures. How to model the cables, their friction, and then how to model the injecting the cables and so on. So okay, I see one last question. Is it possible to adapt the bond stress slip behavior to other materials as ultra performance fiber reinforced concrete steel? Yeah, of course. If you model some high performance material, you will use the same prototype, and you put there. I mean, and you also have reinforcement. Then you can use this kind of models, and of course the bond properties will be significantly higher than in normal concrete. But you can use the similar approach. Okay, so thank you again for your attention, and see you soon at another webinar. Goodbye.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.